Hello and welcome. This is part 6 of topic 3, where we going to look at an application of estimation of an unknown input in the presence of multiple unknown inputs. Particularly, we're going to look at the problem of estimating an unknown input or distributed decentralized unknown input observers for interconnected systems. And so what we are looking at is an interconnected system where, just for the sake of simplicity in our presentation, we consider two subsystems. And the mathematical model of the subsystem 1 is represented by this stacks by model, where we have this local unknown input vector. It's actually a vector. So we can have more than one unknown input. It could have up to Q1 local unknown input in subsystem 1. And we have the stacks vector for subsystem 1, which is of dimension ni. For example, I equal to 1. Ni is an integer number. And the local output vector, the local output measurement vector, is of dimension pi. So we got two subsystems. They are interconnected dynamically coupling by this term in here. That one is the interaction coupling from subsystem 2 to subsystem 1. And similarly, for this term here is the interaction, that the coupling between subsystem 1 and subsystem 2. So this is what in the literature we call it an interconnected system. They can be geographically far away, and the connection is through this term and this term here. It's just like when you have an interconnected power system. They can be geographically far away, and the interaction amongst those terms give rise to instability, performance degradation, and so on. Okay. As usual, we also assume that the output measurement here, the matrix CI or C1 and C2, they're full rank, row rank, and this unknown input matrix, D1 and D2, they also full rank. So this is the block diagram of the scheme that we like to do. So we have this is subsystem 1 connected to subsystem 2, and these are the connection. So we have a local disturbance unknown input vector D1 enter in the system. We have local output measurement y1 of t. Y1 of t, remember, it is a vector. Okay, it's a vector of pi output measurements. And similarly for subsystem 2, we have local unknown input vector D2, and we have local output measurement vector Y2. So that is a representation of an interconnected system. And we have local input in subsystem 1, we have local output vector. Now, the idea of what we call distributed or decentralized unknown input observer is as follows. In the case of distributed unknown input observer. Let's have a look at this observer itself here. This is an unknown input observer. It takes in the output measurement vector y1 of t, which is the local, we call it the local output vector measurement. So we send in this, we take in this local output measurement vector. And on top of that, we also take in the output measurement vector from the subsystem number 2, and we feed it into this unknown input observer. And then we do something about it, and then we generate an estimation of the unknown input vector d1 of t. And in such a way that d1 of t actually asymptotically converging to the true unknown input d1 of t as time goes to infinity. The requirement is that the observer that we design in this subsystem here, it should be insensitive. So in other words, if even despite this unknown input simultaneously affecting the entire system, the observer that we design in this subsystem here estimates asymptotically the unknown input d1 of t. It's insensitive to it. We talk about distributed in the sense that because we need the output measurement from subsystem 2 come into this observer. Now, if we don't have it, if let's say we cross out that bit there, then the only output measurement that can come into this observer is only from the local output measurement vector y1 of t. In that case, if it is possible to do so to estimate d1 of t asymptotically, then that scheme is called the decentralized unknown input observer. All right. Now, this is a very flexible way of considering the arrangement of this scheme. Sometimes we maybe don't need to use all of the output measurement from subsystem 2. Maybe we might only need a few of the output measurement vector, a few of the output measurements. Then we can have partially distributed and all sorts of things. Okay. So likewise, in this subsystem, we are interested. Now, this observer itself is from based in subsystem 2. And so it uses a local output measurement y2 of t. And in the case of a distributed unknown input observer, we take in the output measurement vector from subsystem 1, and we use everything to generate an estimation of the unknown input vector d2 of t. And it has to be insensitive. So this observer here itself is insensitive to the disturbance or the unknown input vector that come into subsystem 1. Now, the term distributed here is clear that you see there is no link. There is no link between this observer and this observer. So they are actually completely decoupled from each other. And so in this sense, if there is something wrong with this system, observer here, this one it can perform independently by itself. And so that's what the overall scheme is about. We can have distributed unknown input observers for both systems, both subsystems. In that sense, we take in the measurement from the other subsystem. When we talk about decentralized, we don't need to use any of the information from the other subsystem coming into the local unknown input observer. So we have a bit of flexibility in there. And the question is, how are we going to do it? The answer for that is yes, it can be done. And it is based on our application of unknown input, which is topic 3. Now, by the way, in the literature, we came across many results on distributed or decentralized stack or functional observers. So they basically focusing on estimating not the unknown inputs, but a stack vector of the local subsystem x1 of t. So in the case of decentralized or distributed stack observer, this observer itself will generate an estimation of x1 of t, or a linear combination, which is called functional observer, which is a linear combination of this vector. And so in the literature, you can see that there are quite a number of results available. Some of those early work talk about decentralized stack estimation for large-scale system, or decentralized linear functional observers. And then later on, there are also quasi-decentralized, more or less like distributed functional observers with application to interconnected power systems and so on. However, to our knowledge, not many results on the asymptotic distributed or decentralized unknown input observers. So in other words, our objective here is to estimate the unknown input vector asymptotically. So how are we going to do it? The answer is yes, we can actually achieve that based on the application of what we discussed so far in topic 3. So I would like to go into the book where there is a particular section in the book. It talk about the design of distributed decentralized unknown inputs for interconnected system. And so we like to take it from the book in here, and we like to take an example on how to go about doing it. There are a number of ways in which we can actually achieve the design of distributed or decentralized unknown input observers. And one way is to take in the global system. In other words, what we do is we augment both of the stack vectors for both systems into one global stack vector. So essentially, that can be easily done because when we got two subsystems like this, we just stack them together, augment the stack vectors together, we form an augmented or global system. Now, the reason why we do this approach can then be shown later on that it might be a better way of doing it. In fact, for this particular example, it's a good way to do it. So we basically augment them together, and that will form a global matrix. We call this matrix A, and then we call this is a vector x of t. And have a look at this augmented D matrix. By the way, for this example, we consider each subsystem has a dimension of 3, which has 3 stack variables for the local system 1. And for system 2, it also has 3 stack variables. We have 2 outputs for each subsystem, and we have 1 unknown input for each subsystem. So this particular situation is where D1 of T is a single unknown input. It can be more than one, but for this example, just for the sake of illustration, we just take it a simple case. So when we augment the stack variables or the stack vectors together to form a global system, then this is the new D matrix, and this is the overall unknown input vector, which comprise two unknown inputs, one for each subsystem. And the output measurement in here consists of 4 output measurements. Now, this situation is where we say, all right, let's design a non-input observer for this system to estimate D1 of T. And in this situation, we're going to use all of the output measurements from subsystem 2. And this one is what it is. That's why we have the new output measurement vector comprised of the local output measurement vector and the other subsystem. Now, if let's say, well, for some practical reason, we might not be able to send 2 of the output measurements from subsystem 2 to subsystem 1, maybe 1 only, or maybe a combination or the sum of the 2. In that case, then we augment the global output measurement vector accordingly. For instance, if there's only one output measurement is sent to subsystem 2, then we have only one row in here. Here in this situation, we're going to use all of them. Okay, so that's why we have Y2 of T. Now, then we just basically having a global system. Matrix A, matrix D, and matrix C, and we basically estimating an unknown input in the presence of multiple unknown inputs. In this case, just the unknown input from subsystem 2. And that's why, as you can see, that we can easily apply the theory or the discussion that we done so far for topic 3. All right. And also in this example, you can see that this is a canonical structure, and we can easily see that when you take C1, you multiply D1, we have this non-zero element in there, which is 1. And we also want to take the output measurement Y1 of the first subsystem and use its first derivative for the decomposition of the unknown input. So when we check the observer matching condition, we can see that it is satisfied. And also you can see that the structure of this row is that this term here is 0. So that means that the first output is actually not reachable from the unknown input D2 of T. And so that means that we can actually pick the first output, which is Y11 of T. This is for the notation where we define the output measurement of system 1 comprise 2 measurements. And so we just use this notation to tell that is measurement vector 1, and we pick the first one. Okay, so and then by following exactly the same process where we do the decomposition, we pick the matrix P and the V matrix. We chose it according to this structure. So we pick the first column, which is D1 bar, which is this column here. And following the process, we obtain V1 is a row matrix. And as you can see, it has this special structure. This is non-zero. We see alpha 1. And then the rest of them 0. And we also have V2. And we pick the E matrix. And we choose the transformation matrix according to this expression. So that bit there is the E matrix. That's special structure because the null space of V1C which is basically that bit there is this E matrix. So very easy. And then this is the column which corresponds to this bit here. So we apply the metric decomposition technique from topic 3, and as a result, we obtain a reduced order system, which has an unknown input in there. So remember that this is a global system where we augmented the two subsystems together to form an overall system, and then we do the decomposition, and we obtain a reduced order system of dimension 5. And there is an unknown input associated with that. And this is the output measurement vector. It's reduced by 1. The original output measurement has 4 measurements. We reduce it down by 1, become 3. And then we also can explicitly express the unknown input d1 of t in its simplest form, thanks to our decomposition technique. So it comprises the first derivative of the first output measurement of subsystem 1. And then also it includes that output measurement of subsystem 1, which is y11 here. So that is the first output of subsystem 1. And a linear function of the reduced order system, which is this one here. So as we can see, it's a straightforward application of our method. And so it's a matter of how do we go about design a functional observer for this system. The answer is no problem. There are so many existing results available in the literature, and we can design a functional observer, which is the one given in here, which estimates this linear function of the stack vector. And so if we go ahead and do it, we would be able to obtain a first order. The good thing is a first order functional observer can be obtained, and the eigenvalue or the metric n is stable. So we come down to this overall observer. So we got the observer z hat the omega plus m y bar of t, and then omega dot is n of omega t plus gy bar plus j1 and all of that from our previous presentation. So the bottom line in here is we obtain a very simple expression to estimate asymptotically the unknown input in terms of the first derivative of the first output measurement of system 1. And here is some codings for that. So this is basically the codings for this example, where we enter all the matrices, submatrices in, and then we obtain, this is basically all the submatrices with C, D, and I submatrices. And then we form an augmented system, which is the global system. And then we obtain the new global D matrix and global C matrix. And the first column of that is D1 by, which is called DD1 in here. And then we obtain the matrix P according to our definition, special structure, and then we obtain the V invertible matrix. And then we also obtain the E matrix and the T matrix. And then we get the rest of the observers, the reduced order system. So we get the rest of the reduced order system. And then we design a functional observer. In this particular example, it is found that we can even place the pole of the observer anywhere we like it to be. The design of a functional observer for this system is a well-known technique, so that's why we're not discussing too much on it. And then we obtain the parameters and we can check all the conditions, and then we run the simulation. So let's run the simulation. Let's cut and paste it, and let's show the simulation. So here is what we done so far. We come up with a distributed unknown input observer where we use two of the output measurements from subsystem 2, and we send them over to subsystem 1. So overall, the output measurement consists of 4 output measurement vector, consists of 4 output measurements, 2 from subsystem 1 and 2 from subsystem 2. And then we use only the first derivative of the first output measurement to realize the decomposition, of the unknown input, and have a look at the simulation here. So what happened is the solid line is the trajectory of the unknown input D1 of t. And the blue dotted line here is just the unknown input. We just make it arbitrarily. It's actually simultaneously affecting the entire system. And the dotted line is the estimation of the unknown input from D1. We see that doesn't matter if there is any disturbance, insensitive. So that's what we meant here. Okay, so it's actually insensitive to the other the disturbance from the other subsystem. And that's why in this simulation, we got exactly the same simulation figure at what's shown in here. And then we can also, if we want to, we can also look at the estimation of the unknown input D2 of t. All right. So in this situation, in here, we're going to say, all right, let's omit some details here. And what happening is we're going to send over the information vector, the output measurement vector from subsystem 1 to subsystem 2. And then we form an augmented global system. And then we design an unknown input observer to asymptotically estimate this unknown input. And it has to be insensitive to the unknown input in subsystem 1. So we omit the detail. It can be done. The thing here is we got this structure. Again, when we look at this structure, the unknown input itself is in terms of the first derivative of output measurement of system 2, the first output measurement of system 2. We take the first derivative of it. And again, it's a reduced order system, first order. It's stable. And so we're going to show the simulation for that situation. So this is the codings when we do the design of an asymptotic observer to estimate the 2 in the presence of disturbance D1. So let's clear this and let's run the simulation. Now, in here, of course, we get the metric N, the metric M, and all of that stuff by designing the unknown input linear functional observer for the unknown input system. And let's have a look at the simulation results. So this is the simulation results for the unknown input in subsystem 2. Now, what we see in here, you see that the dotted blue line is the unknown inputs that enters into system 1, we are not interested in estimating it, but rather we are interested in estimate the disturbance in system 2. So we got this solid line here, E d2 of t. And as you can see, the estimation of that really asymptotically tracks the true unknown input d2. So that basically the application where we apply our results in topic 3 to design a distributed unknown input observer. Now, in the literature, we also discuss the advantage of using distributed observation scheme and all of that. So we can refer to that for further information. Now, the way we approach this design was based on a global approach, which is we stack the two stack vectors together to form an augmented system. So basically, this becomes just like a standard stack space model of a linear system with unknown input, with multiple unknown inputs because of the two vectors stuck together here. And then it's a matter of picking out a targeted unknown input in the presence of the other unknown input. And the decomposition is basically working out what is the minimum number of output differentiators that we can use. Given that the information we selected can be varied from fully transferring the output measurement vector from subsystem 2 to 1, or maybe just a few of them. Now, that was the global approach. Now, the other way around is, as discussed in our previous book, what we can do, we can decompose. We can decompose the interconnected term. So when you look at this interconnection here, now another way to decompose it, there's a simple way for doing the decomposition, and that can be done by a singular value decomposition and so on. But the bottom line here, have a look at this thing. That matrix A12 and the vector x2 of t, which come from the other subsystem, can then be rearranged, can be expressed in terms of, have a look at that, in terms of the output measurement matrix C2 in here. So what we're trying to do here is we split this matrix A12 in terms of two matrices, H1C2 and whatever the rest of them. So together, A tilde 1, 2 and H1C2 should be equal to A12. And this is called the decomposing, decompose the interconnected term into a specific structure where this one involves a combination of the output measurement vector y2 of t, and the rest of them can be treated as unknown input. Okay. So this is another way of dealing with the interaction in here by splitting it into two terms. One is a combination of the output measurement vector y2 of t, and the rest of them is treated as unknown input. And of course, this unknown input, the d tilde 1 matrix is full column rank. So once it is done like that, like for this particular example, when we consider the example, the matrix A12 given in this example, which is this matrix here, you see that it's actually of rank 2. We can decompose that into the form given in here. We see that one there. So it can be easily done. We split that, and then you can see that that bit there belongs to the second output measurement from subsystem 2. And then this bit here is now treated like unknown input. So we reduce instead of dealing with a global system, we are dealing with a smaller subsystem with a smaller dimension. And then the unknown input here, basically we have one additional unknown input, and that one additional unknown input is called the tilde 1 of t. So again, when we look at this system, which the decomposition, it is also an unknown input with local output measurement. However, it also have this measurement from the other subsystem as well. And so it's a matter of going about design an unknown input to estimate this D1 of t in the presence of that disturbance in there. The problem with this approach is when we look at this new matrix, which consists of D1 and this column matrix here. Have a look at that. The problem we're facing is when we take C1 multiplied by D bar, it gives us that sub matrix there, and that sub matrix itself is really not invertible. So the problem we have in here is the observer matching condition is not satisfied. And as well as if we want to just pick one this one estimate D1 in the presence of that, because of this entry here, they all non-zero. So that means that we really in trouble. So in other words, the approach where we decompose the interconnection, sometimes it works, sometimes it doesn't work, but in this situation it doesn't work, and that reinforces that whatever we did based on the global system is a workable option for this example. So as you can see that as a designer, we have a number of tools, methods available for us, and it's just a matter of utilizing, using whichever appropriate method that will help us to go about design the unknown input distributed or decentralized or whatever that we need to do. Right. So that is an example where we show that we did use distributed unknown input observer. Now, the other bit is we can actually investigate where we can completely don't need to use the information from subsystem 2 send to system 1. Of course, the less information that we have, the more difficult the problem becomes. And when we actually try to do that for this example, the previous example, we could not get a totally decentralized scheme because we couldn't design a linear functional observer for it. So here is another way. Maybe we can consider a different matrix for the unknown inputs, like D1, D2 change to something else. This is just for the sake of illustration. This is where we say, okay, let's look at another system. We can try distributed, we can try decentralized structure. And if there is no measurement from system 2 is sent over to system 1, that means that when we augment the two subsystems together, the available information or the output measurement that we can use is only come from subsystem 1, and that's exactly what this output measurement vector is. And if we follow in the whole process, luckily for us in this situation, we can still do the decomposition, and we can still use the first derivative of one output measurement from system 1, and the functional observer turn out to be a higher order than 1. It's actually a second order, but it's okay. It works. It still gives us available option. And bear in mind that when we are talking about completely decentralized unknown input observer, it is really a very stringent requirement because the information available is less. So there's a price to be paid for it, and that basically we have to have a higher reduce order functional observer. Considering the global system itself is a sixth order system, and then considering the output measurement is only 2, so the reduced order system itself is actually a fifth order and one output measurement. So normally, if we do the stack observer for it, it requires a fourth order system. Here we got a second order system. Okay, so I'd like to just quickly show the simulation results for that, and that is for the situation where we have a complete decentralized structure. You see that the metric C in here is just based on the local output measurement of subsystem 1 only. And then this is the simulation code for that. And that's cleared. And let's run the simulation. So we got this some kind of simulation like this, and that basically the one that use complete decentralized information. The unknown input is estimated based on the first derivative of the first output measurement of system 1. The observer cell is a second order observer. Okay. And of course, I would like to leave it to the reader to investigate whether it is possible to do so for the subsystem 2. Maybe it's possible, maybe it's not possible, and we might need to look at for the other option, like instead of sending out the information completely the output measurement and 1 and 2 separately, we might just add them up and just send one over, for example, and so on and so on. In here, we show the case when we do decentralized, but not totally decentralized. We basically only just want to show that here in this situation, the output measurement is basically a combination. You have a look at this. We're sending over the sum. We're sending over the sum of 2 output measurement in one go. That is possible in this situation. That is in fact reducing the requirement for network communication and so on, because instead of sending 2 signals separately, we add them up and we just send 1 signal. Well, it's very intriguing. So basically, we can have many options available when dealing with interconnected systems. We can play around with the idea that we can have a total decentralized information structure, or we can have partially information, and so on. It's all boiled down to the practicality of the system that we are dealing with. But the good thing about the theory is that we can actually apply in our existing estimation of a targeted unknown input in the presence of multiple unknown inputs. So we have our tool, we have our decomposition scheme, and we have the simplest way of design unknown input functional observer. So that concludes our presentation. We had a series of presentation for topic 2 and topic 3, and that basically form the first part of the book. And so the first part of our book is basically focused on estimating targeted unknown input. Okay, so we could have a single unknown input in the system, or we could have more than one unknown input, and we only want to estimate one unknown input, or a few of them. So basically, we're talking about targeted unknown input in a system that has multiple unknown inputs. All right. And so what are our key concepts and contribution? As far as we can summarize, we basically have a novel metric decomposition technique, as discussed extensively so far. Now, that decomposition technique allows us to express the targeted unknown input in its most simplified form. We want to estimate an unknown input asymptotically, and it remains insensitive to the others. So this most simplified form has the least number of output differentiators. And of course, it's also expressed in terms of a linear function of the stack vector. Instead of design a radio order observer to estimate the entire stack vector, we don't do that. We estimate a linear function of the stack vector directly. And doing so, as we have already demonstrated in the examples, we can overcome some of the restrictions associated with unknown inputs. Like for example, we can have the observer matching condition. They don't need to they don't need to be satisfied, as in the case of design an entire stack observer to estimate the entire stack. Or the number of outputs can be less than the unknown inputs. So consequently, the targeted unknown input can be estimated by using minimum number of different derivatives of output and a radio order functional observer. So topics 2 and 3, which is basically the first part of our book, is all about that. And that's the reference from it. And please join me again in the next series of presentations. We're going to have a whole heap of presentations which belong to topic 4, where we will look at how to asymptotically estimate unknown inputs in a wide range of time delay systems. All right. So we're going to extend into time delay systems. And we're going to look at all sorts of time delay systems. And it can be multiple non-commensurate time delays in both the stacks and output vectors. And it's going to be very interesting because when we decompose the unknown input in its entirety, we will come up with a new concept. We will come across a generalized functional, which does not only consists of the function, which is the linear combination of the stack vector. It's also a sum of the linear combination of the stack vector and the delay combination of the stack vector, and so on. So we call it generalized functional. And that's the first time we come across that. To be honest, in the literature, we haven't seen anything like that. And so that leads us into the development of design generalized functional observers to estimate generalized functional. And that's the best way to do it. Instead of just estimate the entire stack vector and to realize the estimation of the generalized functionals. Okay, so please join me in the next topic, where we will look at the decomposition of time unknown input for time delay systems. And we come up with something very intriguing. So thank you very much for joining. and hope to see you again in our next videos.